So this is kind of presentation of several results done in the last more or less 2 years with several people, some my students, some young collaborators in around the world. One is not so young anymore, but you will see his name. And of course, the topic is extremely beautiful and from a mathematical viewpoint, and of course, as you know, from physics standpoint, because of the great impact that the new discovery of condensed matter was done basically at the beginning of this century, but is based on theoretical work that was rooted in Einstein and Bose. All right, so I'll show you my summary. It goes in 3 different directions, but is all mixed up. And so I will warn you when we just turn towards another direction and then another direction. And so I hope to show you something new. The idea is that condensed matter physics is, of course, explained in books, but there are lots of statements that lack proof, mathematical proof. And some of these statements, in particular regarding, as you see here, helicity, have been done in this presentation. So I start with the quantum vortex defects in hydrodynamics, and then helicity has to be reviewed. So apologies to those of you who already know very well this particular aspect, but I need this in order to present the rest. Then I will give you proof of the fact that circulation for these vortex defects is quantized, and the fact that helicity in particular is 0. Then I will move to another topic and then show you aspects of the related to the topological scenarios that we have when we consider vortex motion, and aspects relating 0 helicity and reconnection of these systems. And finally, something that I think would be very useful for applications and technology in the future is a creation of new defects by topological aspects. All right, so just to set the scene, many of you know this, but I'd like to point out that in a superfluid, helium superfluid, not condensed matter, you have vortices that are extremely thin in the aspect ratio, and they form complex tangles. And this intrigued people like me to apply geometric and topological information to analyze the evolution of these tangles, simply because vorticity is highly localized. So there is no diffusion, basically. We are talking about superfluids, and so it's consistent with the mathematical idealization of vortex tangles. This is an old work that we did with Carlo Bareng in this group. 2001, we analyzed this evolution of tangles using linking numbers and other information. And at the time, you know, it's almost 23 years old work. Actually, we started more than 25 years ago. And it's quite an interesting aspect to see the evolution since then. Well, I moved to just show you the production of quantum turbulence in condensed matter physics under the equation that I'll show you. This is one screenshot of many, of course, many works. Now, the interesting thing about quantum turbulence is that it's a kind of mystery that has an energy spectrum that is very, very similar, if not identical, to the classical Kolmogorov spectrum, and this is a puzzle for many people. And then the fact that I probably intrigued Carlos Calobarenghi's group to do work on finding knots and links. I remember the words of Keith Moffat long time ago visiting Japan, saying, Renzo, there's no point to look for knots. At least you go for the trefoil, maybe something more complicated, but they all decay, so you don't get anything more than that. Yes, in classical vortex dynamics, absolutely, I believe that. But in superfluids, it's a different story. So when they look for knots, and this paper, 2019, they found such a complex knots that no knot theorist in the world could analyze. There is a simple way, of course, it's a crude hand, even not a good approximation. It's just a crude hand understanding. If you look of the power of the exponent in the polynomial, the knot polynomial, it gives you an idea of the complexity of the knot. Of course, it's not precise, but it gives you an idea. Well, they got such high exponents that are beyond modern tabulations of knot theory. Now, these knots, of course, they do reconnect, they form, they reconnect, and then they cascade towards, say, simple loops before disappearing. So they follow exactly the cascade that you would expect for classical structures. Point is that they could analyze different knot types, and they developed a knot spectrum. So the idea is to use more and more of these new tools from knot theory to analyze these structures, because they are so localized. That's the important point to take on board. Well, we have here just reminding us the discovery by Cornell, Wieman, and Kettle got a Nobel Prize from this work, and this is 1995. And then came Anderson, where you see all these spots that are representing a system of defects in the condensate. I'll explain what I mean by that technically, because otherwise we misunderstand things. Okay, so I just skip lots of details, and what you get here is a mean field equation for a gas of bosons. So let me just briefly, my way to understand this, offering you a quick way to understand. The system is made of particles, bosons, brought to ultra low temperature, millikelvin temperature. And at that state, the tricky point is that bosons, like photons, are at the minimum energy state obeying one single wave function. That's the point. One single wave, unless, differently than fermions, the bosons can share the same quantum state. And so they are governed by one wave function that I represent here with this psi. Now, if you do a mean field approximation to this quantum system, you get this Gross-Pitayevsky equation that, as you see, is basically a nonlinear Schrödinger equation. You have a cubic term, maybe my pointer doesn't work, but you have a cubic term there, and then the rest is the Schrödinger equation. Psi is the wave function of the system, function of the vector position x and time t, and we assume that the system is in an infinite domain with this condition psi squared going to 1. Now, because this is another little piece of history that is good to remember, because there was a dispute on the faith of quantum mechanics in the 20s, Einstein and few others, Bohm and Madelung, didn't agree with the Copenhagen school. So they went for a predictive theory, and not happy about the quantum developments of the time. And the predictive theory is based on a transformation that is given here. Madelung, in 1926 and 27, the paper proposed this combination of a kind of density, average density of this gas, rho, and then this theta that represents the phase of the wave function. Through these assumptions, rho is just a mod squared wave function. You have a velocity u as a grad of the phase of theta. And by applying this transformation to the Gross-Pitayevsky equation, then you find two equations, and you can interpret hydrodynamically this wave equation. One equation is just the standard continuity equation that we know very well. The other equation, if you look carefully, it resembles in the form the Navier-Stokes equation. Of course, we do not have pressure. We have a pressure term replaced by this density, and then we do not have gradients of the velocity. We have gradients of the density only. So the system is basically simpler, if you like. We have the contribution from this stress tensor and the contribution from this pressure-like tensor term, and the equations are similar to a fluid. So we can use and we can profitably take advantage of the progress done in direct numerical simulations of, say, Navier-Stokes equation and so many other results. Okay, this is the background. Now I want to go back to the fundamentals just because I cannot find in books a good explanation. So this is my explanation. It's not so different from other contexts, but it's, I think, is pointing in the right direction. First of all, what is a vortex in this case? A vortex is a geometrical line, is a line, is a nodal line, is a mathematical nodal line due to the intersection of the isophase surfaces. So it's a mathematical concept. This is the singular line, and on this line, defined by psi equals 0 as intersection of isophase surfaces, then we have the ambient space foliated by infinitely many isophase surfaces. I'm afraid they are not visible because they are in light gray. Imagine that you have a book, you open the book with the spine vertical to your table, and you have this open book decomposition of the space through the pages of the book. Okay, so imagine that all the surfaces are like planes intersecting on this straight line. I'm sorry, I'm getting this message on time to time, and I don't know why. Okay, so the circulation is present because the definition is given here, and we have theta. Theta constant is one of these surface, and grad theta is normal to the constant, to the plane, and so we have this contribution to circulation. That is different from 0, and that is the reason why people talk about vortices, simply because there is a circulation different from 0 there. Then what we have is, sorry, I have a problem with my slides. Okay, I do this. Let's see if it works. Okay, and then I propose the following. Imagine that you have a volume filled by the condensate, by this gas, and then you have this nodal line. The nodal line has no mass on it, no particles. So it plays the role of a hole. It's like a hole in your ambient space. And because it is like a hole, or if you like, an empty tube, the ambient space evidently is multiply connected. So imagine this hole is there, and the vortex line is a Dirac delta distribution on this line, and what you get is the ambient space multiply connected by the presence of this hole, if you like. The theta that contributes to the velocity is, of course, multi-valued, and omega is a singular field, if you like. If you go to the cross section, well, it's again like a hole, and in order to simplify the connectedness of the space, you have to provide a cut, a Riemann's cut. So imagine that the green line is the Riemann's cut that you allow to open and to simplify the space, and there you have your isoface surfaces in light blue, and the cut is represented by any one of these isoface surfaces in green. So I call this cut surface sigma, and imagine that this cut surface is any of your isoface surfaces foliating the space. Then you apply multi-valued theory, and by application of Kleiner theory, you can correct the velocity. You know, the velocity is grad of theta in principle. And then you have vorticity, that is the curl of the velocity. So if you were not able to correct this, then the velocity would be zero. But you have a velocity due to the grad of theta, and so you have to do a little bit of techniques, and by distributional method in this case, you can produce this result. Now, with this result, you are okay, because now the vorticity is different from zero, because you are just apply these definitions. The delta Dirac delta is along the tangent of the nodal line, and then it has a well-defined curl. All right, so these are just the basics. And then by noticing that the phase theta is going as many times as you like around the nodal line, then evidently you have the circulation 2 pi n. This is as far as even a little bit more than what is available on books. I'm going to prove this aspect, and I'm going to prove other things. All right, so helicity. We start with the classical definition of helicity, and this is all of you know this, is u dot omega on the domain where vorticity is defined, and the fact that has been proven conserved quantity in ideal case is a well-known fact that resides in Moreau's work of 1961. Then, as you all know, Keith Moffat made a fundamental contribution in interpreting this conserved quantity in terms of linking number, and then I joined the project in defining a kind of correction or completion to this formula. What we have here is that the integral quantity, u dot omega, it can be expressed in terms of two topological quantity, the Gauss linking number and what we call the self-linking number of a single component. If we consider a component, a link, a system of vortex knots forming links. The gammas are the circulations of these vortices. Now, this is from a classical viewpoint, and I didn't write the name, but Haider Salman in recent years, I think was 2016, something like that, proved that the same topological interpretation of helicity could be given to quantum cases. All right, so this is a single element, a knot, if you like, and for this knot we can define, for this link, sorry, we can define a Gauss linking number that measure the linkage, the topological linkage between these two elements. If we have a single component, however, we need to add what we call the Calugariano-White self-linking number. Calugariano in 61 proved that this quantity is a topological quantity. You see the difference, we have an Ri here. It refers to the fact that instead of a curve, imagine the axis of these vortices, you have a ribbon. A ribbon means that your vortex has real thickness. And because of this, you can decompose further the self-linking number into two quantities that are of global geometric character. So on your, say on your left-hand side, you have a topological quantity, and this topological quantity, I remind the young people, topology means that the quantity does not change under continuous deformation of the structure, but the self-linking admits a decomposition in terms of global geometric quantities that, of course, are not conserved during evolution. The first is the rise, and the second is called the twist associated with the ribbon. If you think of a ribbon based on the axis of your vortex, then the rise gives you an information on the folding of this ribbon in space, whereas the twist takes care either of a localized torsion or a combination of torsion and rotation of this ribbon along the axis. Now, I anticipate, because I couldn't put too much on my presentation, that the ribbon is, if I'm talking about quantum systems and quantum defects, the ribbon is a piece of surface on the isophase surface that determine the nodal line. So we can talk about twist. Now, under GPE, we assume that everything is smooth, otherwise we cannot do any analysis. And so I consider an initial position A that is brought to position X by a diffeomorphic flow map. And the proof is, the result is the following under GPE. The kinetic helicity is a conserved quantity, and not only conserved, but the helicity, the total helicity is 0. Now, in order to prove this, I sketch some steps, because it cannot be done in 2 slides, but I want to do it in 2 slides. We start from a GPE Lagrangian, and there is the expression of the action. You see here, you have the velocity. Remember, the velocity is grad theta plus the contribution of from the Dirac function, and then a function of the density. And then by doing this, you just expand the squared, and you get this expression. Now, this expression, look at these 2 terms. You have one term here and the other term here. And what you can prove is the following. As regards the first term, you can use the divergence theorem for this term here, and you reduce it to this. And this is just the expression that you get for a theta that is considered on sigma. But sigma, the cut surface, is any isophase surface, so is a constant with respect to time and space. And the second term also remains constant. The other term, this one, you can prove by using some of Kleiner's calculation that is also 0. So you reduce further this action to the action that you see below by absorbing these constant terms in there, and the fact that the derivative of delta squared is 0. So you have now end up with this expression, and this expression can be read out by a kind of Euler density, action density, that is a standard thing, plus a contribution from the phase that is expressed by this term. So you split this action into parts, and by variation of the action, you can apply another theorem to look for the charges. So the charge of the GPE is made of 2 quantities. One you can recognize it as, let's call it an Euler charge, and the other part is due to the theta contribution. Now, I rely on some of the work done by Yasuhide Fukumoto. First of all, I consider eta, the displacement, and the displacement of particles going around on a loop encircling the nodal line. So this is basically obviously giving you the conservation of circulation, gamma GPE, and because of the delta function contribution, you see that it gives 2 pi n, where n is any natural number. Now, remember, we tend to talk about a circulation equal to 1 or 2 pi, because n higher than 1, for some reason that I believe interesting to investigate, physically, defects with a higher charge are known to be unstable and decay to defects of single charge. But again, this is another aspect that is physically so, but there is no piece of mathematics that proves this. So it's also an interesting challenge for the young people. Now I go back to the work of Yasuhide when he considered the charge in the Euler case, and now eta is a different displacement. It's the displacement of the particles that are winding around the let's say the vortex line, and you can rewrite these in terms of Levi-Civita tensor, and then with some algebraic manipulation express this in J being the Jacobian of the transformation in initial position with respect the final position with respect to the initial position. You express that as a U and omega, the vorticity. And so you get this charge, the GPE charge. You refer to up there, you substitute U with your grad theta and delta, and what you're left, because of the minus contribution, you are left with the delta contribution. And by just obvious manipulation with eta, you can reduce this to this quantity, delta sigma in omega. Now, you consider, again, a little bit of algebra. You have your nodal line, and you consider any volume or infinitesimal volume associated with these isophase distributions. Imagine that you take 2 that include sigma. You can take an average of delta function on sigma, and then you can prove that what you get for any volume is this result. And the expression of the charge is in terms of the divergence of omega. Even if omega is just expressed by Dirac, you can still show that is 0. And so you end up with the fact that your QGPE is basically reducible to the standard form of helicity, because you remember is made of 2 contributions. The grad theta, the irrotational part, does not contribute, so you are left with the delta distribution contribution, and that is 0. So this is a proof that helicity is 0 for these systems. However, back in 2015, 2016, from direct numerical simulations was something known, was a fact. People found that helicity was always 0. And I remember some jokes with me, said, what's the point to look for something that is 0? Of course it's conserved, it's 0 by definition, so it remains conserved. It's like a property that we give sometimes to other people upstairs. You cannot see it, so it's conserved. Well, actually, the fact that it's 0 and that it is conserved is very interesting, and you will see why. Anyway, this is what we have so far. Now, as I said, the proof that was 0 is already available from other papers and older papers. Here we have a cascade of a hop defect, a direct numerical simulation done by Simone Zucker, and as time goes on, you see that the system reconnects. It does, it changed topology, it forms a loop, and then the loop decays to smaller and smaller loops. This is a very well-known process. It reminds us of other processes that I'll show you in a moment. If you want to check about helicity, you see this is the work of 2017. It was done, and the total helicity is there. And then we did a lot of numerical check to prove this. Of course, the Rife goes down and is balanced by the twist, and plus the black dots shows you where a reconnection takes place. You can be much finer in your analysis, showing that at each stage that is the case. So at each singular state between reconnections, you have a balance of Rife and twist plus linking number, of course. All right, so this is the state of things. And then you have this cascade, and now I'm moving in another direction. Now I'm considering the fact, okay, so we have assured the fact that there's a proof that helicity is zero, that circulation is quantized. I don't have a proof that it is unstable for higher n, but this is the case. So I will assume from now on that circulation is only 1, or if you like, 2 pi. Okay, the standard assumption. And then I want to compare this evolution to known evolutions in classical physics. And one example is obvious, and is thinking of the result of William Irvine's group on the evolution of a trefoil knot. There is a little remark that I am happy to make, and that they produced this knot, and the topology was inherited from the topology of the airfoil. So, of course, it was a remarkable result, but it's not exactly quite I wanted to do. I conjectured the way to produce a knot from unknotted, unlinked filaments, and I'm going to show you this result, which I think is interesting, especially for young people. I'll tell you why in a moment. Anyway, what we see here is the production of a trefoil knot, and then is in water, and is visualized by vapor bubbles, tiny bubbles, and then it evolves, and down you have a drawing of the topology, not the geometry, the topology, and you can identify, as the authors did, the fact that the trefoil knot decays, so to speak, to a Hopf link, and then a one single unknotted structure. Of course, it's very hard to see. It is highly convoluted. It goes up, and then it goes down, etc. And then it further decays down to a number of loops. And then, of course, it's dissipation killing off everything. Now, more or less, you see that this sequence, I can show you also the trefoil, but this sequence is similar to this one. Okay, so you have a jump from, say, a link, an unknot, 2 knots, and 3 loops and 3 loops. Here you start from here on the above, but you can start also from the trefoil. So I want to show you, first of all, reproduction of results known in classical fluid mechanics. This is, many of you surely remember the beautiful work, experimental work by T.T. Lim and Nichols, as a Nature paper in '91. And we just provided the same results by running Gross-Pitayevsky equation with numerical simulations. Basically, the blue tube that you see is just a way to visualize the nodal line. Otherwise, it would be tricky to understand what's going on. The blue tube represents more or less 1/100th. Sometimes, of course, you go finer, 1,000th of density of 1, or density 1 at infinity. It's just a visualization technique. And then you can see the points of reconnection and the production of rings. And all the times these systems are freely evolving, they produce as a final stage lots of loops, unlinked, unknotted loops. We went to investigate many knot types, And here you have one, in particular, the more complex that you see in this slide is the 2-9, is going twice around the large radius and 9 times along the azimuthal direction. And the evolution of the 2-9 is beautiful. You see the production of one single loop and then smaller loops. I think I have a video to show you. I hope it works. Let's see if it does. You see there is a rotation and then reconnection, and then finally instant reconnections. So, you know, why you have one production of a big loop and then production of many looplets instantly? Well, because of the symmetry of the system. The system is highly symmetric, and of course, reconnection take place exactly as you expect they do. So the idea is, well, you are not going to see anything so special if you start with a highly symmetric configuration. And I wrote many years ago, my conjecture was to make 2 elliptical ring reconnecting. And if they are elliptical and slightly misaligned, then the curvature is different from one location to another. So you break the symmetry, the space symmetry, and then perhaps you have reconnection at different times and locations in space. So you may get something else. Now, this is the movie. If we want to check properties, of course, it's easily done because it's in a computer. You extract your data. You have the peaks in light blue of total curvature, and you see the different rise, the different rate of these peaks before and after the reconnection, denoted by these black dots. This is a signature of the irreversibility of the process, because the GPE itself, remember, is a mean field equation, so it is reversible. But the reconnections are local in space and time, so that's why. Okay, you have, of course, in the usual check, this is done on the 2-9 knot. Similar plots are available for all the knots and links we tested, and similarly for helicity. You have a 0 helicity and contribution from writhe and twist as expected. All right, well, this topological cascade is the only scenario you expect? No, of course not. In nature, you have all sorts of complications. You may have different scenarios as well. What's the point to have different scenarios? The point is you can have unexpected dynamics, but on average, what you get is a continuous decay towards formation of loops. So this is the message. However, at particular instances, you have reverse dynamics. Here, you have a cycle, 3 loops, 2 loops, 1 loop, and then, why not, going backwards. Similarly, for the formation of a trefoil knot, remember the experiment by William Irvine. You start with the trefoil knot and you see the decay towards loops. But we are doing computer simulations. We can prescribe the initial conditions at will. And what is the result of a particular meticulous prescription? The prescription is you start with 2 unlinked loops, and then you have you go backward in that cascade. You have a formation of 1 single loop, then the loop reconnects at one place, it forms a hop link. We just go reverse in the cascade I showed you before. And finally, you get a trefoil knot. So this is the simulation, and I hope it goes. You have 2 unlinked, unknotted curves. They link together to a loop, to a hop, and then finally to the trefoil. So the message for the young people and for me is the following. Initial conditions are extremely important. Why we don't see this naturally occurring? Because it's highly improbable. That's all. It's a probability question. How likely is it to get a trefoil by shooting 2 elliptical loops. And this is the difficulty of Kelvin. Go and read Kelvin. He spent 1 year with Tate to produce a trefoil knot or a link unsuccessfully. Why? Because they had to gauge the exact initial condition with a box, with an orifice, with some experimental apparatus, and that was extremely hard for them to do. With the computer, we can do that. We can play with the geometry. We know LIA. We know first crude approximation of Biot-Savart. We can guess what is the right initial condition. So this is another message. Okay, so now the proof that total helicity is conserved can be given, as I did, by, say, distributional techniques, but it was given by Dewitt-Sumner and Ilsma Kruiswijk based on topological methods. So if you use obstruction theory, it's a piece of topology, topological theory that is really advanced, you can prove that the contribution of helicity of a single component is 0, and the contribution of total components is also 0. So this is for one component, I equal 1. You can prove that self-linking plus the eventual linkings of other structures is 0. Now, how do you read this? You can convert this to a linking matrix, and this linking matrix has a diagonal with self-linking numbers and Gauss linking numbers on the other. Remember, the matrix is real and symmetric because LK12 is equal to LK21. But the interesting case is that the sum of all row components or column components is 0. So these matrices, or the algebra of these matrices, is very, very unknown, is very little known. I circulate emails to a number of people in the world, and people in statistical theory, etc. This is very specific type of matrix, but it's quite interesting from my viewpoint because you know, is real symmetric. You can transform it into a proper reference system into diagonal form. So you would have, ideally speaking, a diagonal element made by self-linking number. And what that diagonal form represents is a mystery. So I don't know, but let's leave it out for the moment. Now, what we have here is the possibility to produce a number of results, and under anti-parallel reconnection that is typical of this phenomena, as it is for classical vortices, we can prove that across the reconnection process, Reith remain conserved. Don't take me wrong, Reith, of course, is not conserved over the whole evolution, but during the reconnection, just before and after, Reith is conserved. But then we have the self-linking is 0 for a single defect in isolation. If it is 0, then also twist is conserved. Under helicity equals 0, antiparallel reconnections conserve total twist. Now, total twist is made by 2 contributions. Sorry to bore you with the geometry. Twist is actually decomposed into total torsion and intrinsic twist, which is the amount of twist that the ribbon does with respect to the center line. So you can say that also intrinsic twist is conserved. And why I care about intrinsic twist? I care because I want to pay attention, not in this talk, to surfaces whose boundary is the nodal line. And it's like soap bubbles. Surface is an isophase, and the surface, if intrinsic twist is conserved, then under reconnection, the surface bounded. So imagine these 2 surfaces are now going through reconnection and form one single surface. Through reconnection, the surface orientability is preserved because the intrinsic twist is also preserved. Okay, now I move to the last topic, and that is considering one single defect. And this is done in laboratory with a lot of difficulties, but has been done recently. And so we have one single defect. Linking number is 0. There are no other defects, but the self-linking is equal to 0. So the immediate consequence of this is that a single vortex defect of self-linking different from 0 cannot exist in nature. All right, so if it cannot exist, well, we are scientists. They tell you, don't do this, and you want to do it immediately because it's interesting to see what happens. And this is an easy game. And so immediately we wanted to explore what happens if I force the system to disobey this condition. No harm to do that. Okay, so we did a little bit of work. Instead, thinking of your nodal line with the isophase surfaces all around it, imagine to superpose on the system a phase twist or a twist due to a phase superposition. Imagine that this twist goes everywhere in space. So, of course, it's a global aspect. And when you do this, you have to modify the wave function, and you just add this theta twist, the twist phase, and then to the background psi 0, and you get a modified Gross-Pitayevsky equation. It is still a Gross-Pitayevsky equation. Don't you worry, it's still nonlinear Schrödinger equation, and there is a little bit of complication due to these contributions. But with that equation, you can use and derive a number of facts, and this is a little remarkable fact. The Hamiltonian associated with this modified GP is non-emission. And if you check on non-emissionity in science, you see that now people has plenty of interest in that respect, because despite the fact that the standard GP is reversible, here you can show that under certain conditions you have a possible absorption or release of energy or other form of energies. So you can derive an instability criterion. I just cut a long story short, and I just give you this information. If twist diffusion is present and is represented by this factor, then you have either the Laplacian of the twist phase less than 0, linear stability, or a diffusion that provokes an instability. So imagine you have your nodal line, you superimpose from exterior sources twist, and you see what happens. And what happens is this: you have a topological instability. The defect cannot sustain this twist because it's disobeying the helicity 0 condition, and instantly a new defect is produced. And why is produced this new defect? Because it has to compensate twist right and the linking number that was absent before. So a new defect is produced in time. Now I'm going to show you this by 2 rings, and the simulation is a kind of trivial simulation, because the new defect is produced instantly. As I click the button, you see immediately this. Of course, I could slow down this, but it's just numerics. So it's the time that takes from the wave function at one point to be distributed in the space. So that's the elapsed time. But otherwise is instant. So we have these 2 defects, and imagine that this ring has one twist superposed. So the linking matrix has one row or one column that is not 0, so it's not satisfied. And as I click, you will see immediately a new defect form. Now, if a new defect is formed, now I go to the next slide, then what you get, you have 3 defects. And when you get to check your linking matrix, the new linking matrix with the three elements present is okay. So the new defect absorbs part of the twist present in in the first ring. And then if you let it go, this you can do, and you can see and watch what happens. Of course, there is a reconnection. And then when you get after the reconnection, I just cut it on purpose to show you just the instant, but of course it's a continuous movie. You go a time later than reconnection time, you go back to two defects, this one with the 8 shape and the other one at the center, which satisfies again the linking matrix condition. So if you let it go, it goes like this. Right, so I'm towards the end of my talk, and I want to leave you with another case, and I have to warn you because what you're going to see is a total conjecture. I have no proof, it's just an idea. And we live with new ideas all the time, at least I do. And so I want to propose this idea. We tried numerically to implement this, and we didn't succeed. So we don't know, either the idea is a total bad idea, not to use a bad word, or maybe it needs further work. So the idea is the following. You know, sometimes you travel and you don't sleep very well over the night, so you think, and this is terrible because either you come up with a very bad idea or maybe some good ideas. And the idea I want to tell you is the following. Before, what we had the twist present globally. Now, what about if I can confine the twist locally? How local? Very local. How very local? In the tubular neighborhood of the nodal line. So in the region, we call it, or they call it healing region, in the region where almost the nodal lines becomes physical, where particle starts to be present there. And if you confine the twist there, the idea is, suppose you are far away. You're far away, you don't see any twist, but very locally you have twist. What happens if you can manage to reach this situation? The twist of a single defect, of course, makes the situation unstable, and you expect some dynamics. So this is the idea, and that's it. Okay, you see your point defect there, and all the isophase surfaces in the cross sections are straight planes, so to speak, straight lines. There's no twist. But then imagine that you are at the level of an Armstrong. You are so small, not me, that you go there and you can see almost on the nodal line what happens. And this is the idea. You enlarge, you zoom in, and the more that you zoom in, you start seeing, you know, when you are here, the isophases are perfectly okay, no twist. But imagine that very locally, you start seeing some spiraling and some twist. So the twist, imagine that is localized, only there. And then you take your assumptions due to the criterion that gives you instability. You assume this Laplacian greater than 0, and then twist different than 0 for, say, a straight line or a ring. And then the open question is, would you expect conversion of a twist to writhe? Well, this is known to happen for some theoretical models, you know, high energy physics, etc., etc. People apply this to a number of cases, and they found this possibility. So I came up with, say, a function. Imagine that you have a twist phase that is localized on the nodal line. So there is a GS, two combination of two functions. These are just made up from mathematics. And suppose you have something like this that decreases and goes to 0 critically outside this healing region. And then what happens? Well, you can do mathematical plots of this, and that's okay. If you were able to expand this ribbon away, you would see that it does exactly what you expect it should do for 0 twist. And then this is the conjecture. Would we expect something like this? This is a picture taken by an old paper by Paul Sutcliffe. And, you know, of course, this is a different topic and in different directions. But imagine that you have a rubber band that has some twist, and this twist is unnatural. You force the rubber band with some twist, then what it would do? It would go to a writhe configuration. It would convert immediately the twist towards writhe to balance a twist. Of course, it wouldn't go to full writhe because also that is a wrong statement. It would go to a balance of half a twist compensated by some writhe just to balance things out. And with this conjecture, I leave you. I stop here. Time is up. And I thank you very much for your attention.